All right, so today we are talking specifically about solving word problems by writing equations. And the last lesson had us writing equations, graphing, and making a table. But by far the most efficient is writing an equation or solving an equation if you're trying to get an answer to something. So we're going to start with, just changing from words to the algebraic notation. And we're going to wrap up by talking about the relationship between distance, rate, and time, which you probably have already heard about before in science class as well. Match each mathematical sentence on the left with its translation on the right. Make sure your team is in agreement with each answer before moving on. So what I want to do is actually read the sentence and then figure out which of the equations go with it and why. Clearly, you can see I already have them marked. That's fine. Still a very short discussion. A zoo has 2 fewer elephants than zebras. So somewhere I'm looking for subtracting 2. So if you have a multiple choice and you want 2 fewer of something and you look at your choices, C is the obvious choice. But let's see what else. 5 times more monkeys than elephants. So we just said elephants was 2 fewer than zebras. So that's probably the Z minus 2. And then 5 times more monkeys than elephants. Well, if Z minus 2 is elephants, then 5 times Z minus 2 would be the monkeys. And this Z at the front would be number of zebras. So that is, in fact, scenario 1. 2, Zola earned $30 by working 2 hours and receiving a $12 bonus. So the $12 bonus is something she only gets once. And the working 2 hours is this something that happens over and over. So I would expect to see 2 next to a variable and then adding on an extra $12. And that would be A. 2 times, and we don't know how much she's making per hour, so that's what Z is going to stand for. And plus the $12 bonus equals the $30 total. 30 ounces of metal is created by mixing zinc with silver. The number of ounces of silver needed is 12 times the number of ounces of zinc. So I'd be looking for 12 times a variable, 12 times the ounces of zinc, and then you've got to add in the zinc as well, has to add up for a total 30. So that's scenario 3, goes with D. And Eddie, who earns $5 per hour, worked 2 hours longer than Zach. So I would be looking for Zach plus 2. And so I've got that in B, Zach plus 2, and he's getting $5 an hour. And then Zach, who earns $12 an hour, that would be your 12Z. And that would be scenario 4 going with option B. Now you'll notice that I've highlighted mine, and that's because we are going to look at the let statements that goes with each one. Mathematical statements like those in the left column of problems 631 are easy to understand when everyone knows what the variables represent. So guys, you notice every single one of those used the letter Z. So we would need to know what Z stands for because it's different for each one. What we're going to make is something called a let statement. Previously, we have talked about that as define the variable. We keep telling you to define the variable. Tell us what letter you're using and what it stands for. Technically speaking, that's a let statement. So in the yellow one, 2Z plus 12, this is Zola making money. The Z is her rate of pay, how much she's making in dollars per hour. And so we're going to do 2, because you worked for 2 hours. And I'm going to highlight the dollars per hour because we need to have that in there as well. 2 times her rate of pay plus the $12 bonus equals 30. Well, in scenario B, that was Eddie, who earns $5 per hour, worked 2 hours longer than Zach. So Z stands for how long Zach worked. Let Z equal amount of time Zach worked. Notice that I put the hours on the end. You also could write let Z equal hours Zach worked. And then you wouldn't have to put the hours at the end. And those are both acceptable as long as you have your units. So Zola's rate of pay was in dollars per hour. Zach worked, and he's working in hours. C is the first scenario. The zoo has 2 fewer elephants than zebras. So we did Z minus 2. Z stands for number of zebras. Now, number of zebras is discrete. We count zebras. We measure time. So the number of zebras, that is going to not need an extra unit here because we're not measuring. The things that we measure, those are going to be your continuous. Those are going to be your, curves and lines that connect the dots. But we either have 1 zebra or we have 2 zebras or we have 3 zebras because we count them. D is scenario 3. 30 ounces of metal is created by mixing zinc with silver. The number of ounces of silver needed is 12 times the number of ounces of zinc. So Z stood for weight of the zinc. You could also say ounces of zinc. But either way, ounces needs to be there, either at the end in parentheses or worked into your let statement. All right, next. 1 equation or 2. Elsie took all of her cans and bottles from home to the recycling center. The number of cans was one more than 4 times the number of bottles. She earned 12 cents for each bottle and 10 cents for each can, and ended up earning $2.18 in all. How many cans and bottles did she recycle? Solomon wants to solve the problem using just one variable. Define a variable using a let statement, then write an equation that Solomon could use to solve the problem. So what we're going to do is we're going to look back at the question, and it says the number of cans was one more than 4 times the number of bottles. So we can get the cans if we know the number of bottles. So we're going to let B equal number of bottles. Remember, it's discrete. It's something that we count. So I don't need another unit. We count the bottles. So technically that's your units. And so this sentence, the number of cans was one more than 4 times the number of bottles, that's going to work in as part of our equation. It says she earned 12 cents for each bottle. So no problem, 12 cents for each bottle. Notice it looks like money, right? 0.12 plus 10 cents for each can. Now we're not going to put C because we only wanted to use one variable. The number of cans was, or think about is, there's your equal sign, one more than 4 times the number of bottles. So that's the 4B. And in total, $2.18. So solve Solomon's equation and answer the question in the problem using a complete sentence. So if we want to solve this, the first thing I'm probably going to do is distribute that 10 cents times the 1 and times the plus 4B and get 0.10 plus 0.40B equals the $2.18. You could have subtracted the 0.12B first and brought it over to the other side, but it turns out that doesn't help. That doesn't actually make it any better because here I can combine them on the same side and get 0.52B plus, and there's your 10 cents equals $2.18. If I take away the 10 cents from both sides, 0.52B equals $2.08 and divide by the 0.52 and I get B equals 4. So when it says solve the problem using a complete sentence and you go to start writing your sentence and you say there are 4 bottles, you still need to finish the thought because we need to know how many cans and bottles did she recycle. So we can't finish that yet, right? There are 4 bottles and we don't know. So we need to go back and say, well, the number of cans was represented by 1 plus 4B. So I would do 1 plus 4, and we found that there were 4 bottles. So we know that there are 17 cans and a period, and we would be done because that would be a complete sentence. There are 4 bottles and 17 cans. Marcus wants to solve the problem using 2 variables. Define your variables using a let statement. So this time we could let B equal number of bottles. And if you didn't already know, that hashtag symbol can also stand for the word number. Let C equal number of cans. And now we can write a can equation. The cans are equal to 4B plus 1. We can write the other equation, 0.12B plus 0.10C equals the $2.18. So this is worth number of bottles, this is worth number of cans, and this is our total. But then in order to solve it, you would have to substitute the number of cans into the second equation anyway. So it is slightly more efficient if you can write it in terms of one variable to begin with. Sometimes that's just not doable. So the follow-up question, do Solomon's equation and Marcus's equation represent the same problem? Yes. They both show price of cans plus the price of bottles. And we can also say they both are equal to total money. And they're both going to solve and give you the number of cans and the number of bottles. If we wanted to double check, it says show that your solution from part B makes both equations in part C true. So we can do, in order to get the number of cans, 4 times the number of bottles plus 1. In order to get the number of cans, 16 plus 1 is 17. And that's the answer that we got the first time. We can also double check that if we do 12 cents times 4 bottles and 10 cents times 17 cans, do we in fact get $2.18? It'd be 48 cents and $1.70 which is in fact $2.18, and they come out equal. So no problems there. Either way, the either single equation with one variable or the system of equations will work and get you the same answer. All right. So 6-34, after reading about earning money by recycling, Solomon and Marcus are excited to do some recycling themselves. Solomon has some electronics his parents said he could recycle. Marcus has permission to recycle some small household appliances. They looked online and discovered that the local recycling center offers 60 cents per pound for the appliances and $1.50 per pound for the electronics. But there's a $27 hazardous waste fee that has to be paid to recycle electronics no matter how much you recycle. So recycling electronics is the one that comes with the fee, that $27 fee. So if we said Y equals, I get $1.50 per pound, but they're going to take away a $27 fee. And Marcus recycling the appliances is getting less. He's only getting 60 cents per pound, but they're not taking away any kind of a fee. So in both cases, when I define the variable, I was defining them as Y equals money paid out or money earned, either way, and that X equaled pounds of recyclables, CL. And I think that's right. And the reason that I use the same variable for both of them is because I actually knew ahead I was going to ask you to find out when they earn the same amount of money from the recycling center. So I can set those equal to each other to find out when they're the same. Now, X was pounds. So when will the pounds of electronics and the pounds of appliances yield the same amount of money paid out? So if I wanted to take away the $1.50 X from both sides, I would have negative 27 equals negative 90 cents X. Divide both sides by the negative 90 cents. And I would get X equals 30, or 30 equals X. So that would tell me that X equals 30 and X is pounds of recyclables. So I would say X equals 30 pounds, but I still need to find Y. So I could go back into either of those equations. The faster one is the 0.6 times 30, and you would get that Y equals 18. You should get the same answer for both. So if I did $1.50 times 30 and then took away the 27, I would get $45. Take away the 27, and Y is still 18. So Y would equal 18 pounds. And the one thing that I realized I'm missing money paid out, I should have somewhere that we're measuring that in dollars. And the reason for that is 0.60 is 0.6 of a dollar. And so I do need to say that my money being paid out is in dollars. Both come out with the same answer, as they should, because we set them equal to each other. If both of them turn in 30 pounds, 18 pounds, they will both walk away with $18. Somebody was going to catch me on that one. I'm glad I read it back to myself. All right. The last one that's there is talking about some distance formulas. And they're pretty straightforward when you're younger and you've been given the rate and the time. And the first few examples that are here, it says Morgan decided to take a bike ride. She left at a speed of 16 miles per hour for 1.5 hours. So that just makes sense, right? We would do 16 miles per hour times 1.5 hours and get that the distance was 24. The second example, Morgan's dad drove 20 miles for 0.4 of an hour. So 20 times 0.4, he went 8 miles. Those are the ones that are really straightforward. When Morgan's dad returned from the store, he went for a jog. He jogged for 1 hour, 15 minutes. Be very careful that you're using this in terms of hours. So you can't say 1 hour, 15 minutes, and you can't say 1.15. 15 minutes is a quarter of an hour. So you're going to go with 1.25 hours. A pace of 4.8 miles per hour. So 4.8 times, 1.25. Again, this is the same setup, right? Where we're just doing the rate multiplied by the time. And in this case, we would get that it was a distance of 6 miles. So each of the parts involved 3 units of measure. You were given 2, and then you calculated the third. The 3 units are distance, rate, so that's your speed, and time. Now, time doesn't have to be in hours, but since all of these were miles per hour, miles per hour, miles per hour, they were being measured time in hours. Write a single equation that models the relationship among these three units. It is distance equals rate times time. And you'll notice up at the top, I have D equals RT, and that's how most people remember it. C, Taylor, Morgan's older sister, will be driving from her house to the campsite tomorrow. She averages 65 miles per hour for the trip. It is 195 miles from her house to the campsite. Use the relationship from part B to determine how long it will take Taylor to drive from her house to the campsite, and don't forget to write your let statement. So we're going to let T equal time in hours. And so if we're going to set up D equals RT, we're going to say the distance is 195, and that equals the rate 65 multiplied by the time. So we would need to divide both sides by 65, and we would get 3 equals T, or 3 hours. I didn't have enough space to do that vertically. Normally, you would do that entire problem vertically.